Hello and welcome to this video on Addition Polymers, and what we're going to do today is have a look at polymerization reactions. Let's start with the definition of a polymer. A polymer is a long chain of monomers that are joined together, and addition polymers are joined together when double bonds break and join the monomers together. So let's have a think about some polymers. Some of the polymers can be natural, so natural polymers, examples of which might be silk, for example, or DNA. And they might be man-made or synthetic. And synthetic polymers, let's say going back to the 19th century, synthetic polymers, you made hard rubber, an artificial silk, and then in the 20th century we had new polymers such as nylon and Kevlar. Nylon as in clothes, Kevlar as in bulletproof vests. And then we're still developing polymers now, which would be either cheaper than the existing polymers being used, or they perform their function better than the existing function. So still lots of development going on by the petrochemical companies. That's the chemical arms of the oil companies, who are the manufacturers of these plastics, and they're the ones that are developing the polymers even further. Now, I know you're quite familiar with addition polymerization already, so I'm going to summarize on the next slide the type of questions that you're going to get and how to answer them. So when we get a polymerization reaction happening, we've got monomers joining together, and this is how we write the equation. We write the monomer out. So let's take this simplest example, which is ethene, and we're drawing the displayed formula of ethene. And we say that we have N molecules of ethene, and then instead of writing big long chain of polymer, what we do is we use brackets, like so. We put the repeating unit, which is in ethene's case is this, and we put the brackets that sort of cross the bonds that join the repeating units to adjacent repeating units. And so we have, if we start with N monomers rather, we end up with N repeating units, which is how we write the polymer instead of having to write dozens of carbons. Now here we've got the simplest one, but we could also have different alkenes, where one of the hydrogens might be substituted for a different group, and then you're going to get different polymers with different properties. But what we're going to do now is look at the three types of questions you can get on the addition polymerization reactions. This is the first type. You know, if you have this monomer, what does the polymer look like? Now we're going to have a look at the second type of question you could get. So you could get a question that starts off with the polymer and asks you for the repeating unit. So here's a polymer. So we've got carbon chain here, and it's one of the hydrogens substituted for, let's just say, a methyl group. Just one methyl group, so all of these are hydrogens. Okay, so that's our polymer, and they're going to give you a section of a polymer like that, and they might ask you to have a look and see what the repeating unit is. And you have to look at the chain and see which bits repeat. And you can see, if I just change to red, you can see that this section here that I've circled in red is the same as this section here that I'm circling around in green, right? So so you can see that that's the repeating unit. So then what you would do is you would write out the repeating unit just on its own. And you have to join your, you have to include your bonds that complete the carbon's 4 bonds. So that would be the repeating unit. That would be the repeating unit like that, and that would be the second type of question you would get. But you also might be asked to define what the monomer would be from a repeating unit. So if let's use that repeating unit there. We've got 2 carbons with a methyl group on it, and the rest hydrogen. So just one of the hydrogens substituted for a methyl group. That's the repeating unit, and you might be asked for the monomer. How you get the monomer is that you're going to add a double bond in between the 2 carbons, all right, because this is addition polymerization after all. So you're then just going to have, on the left hand side, you're going to have this hydrogen here becomes this hydrogen here. This hydrogen that I just circled there becomes this hydrogen here. You're going to have a methyl group on this one, and you're going to have another hydrogen here, which was that last 4th one there. So that's the monomer, and you can see that that's propene. You can see that that's propene, and that's the third type of question that you get. So you see that we've lost the bonds that join the repeating units to adjacent repeating units, and instead we've got the double bond in between the 2 carbons of the monomer there. Okay, so that's it. That's the type of questions you get on addition polymerization reactions. The other thing that we're going to do in this video lesson is to look at the properties of polymers, and we're going to look at 3 particular plastics that illustrate different properties. So one feature of all addition polymers, pretty much all addition polymers, is that they're unreactive. So because although the monomers are unsaturated, they have a double bond, and that makes them quite reactive. Once they've taken part in the addition polymerization reaction, they're saturated, and they're also generally non-polar, which makes them very unreactive or chemically inert. So I'm going to put generally chemically inert. And that's good in some ways and less good in fact very bad in other ways, in that these plastics are accumulating in our oceans and being eaten by the fish and causing all those problems that are hitting the news just now. Okay, so that's the first property that we will be familiar with already. But let's go on to have a look at density. And to do that, we're going to have a look at the example of polyethylene. Polyethylene. And so this is the polymer that's just got lots of carbons, lots of hydrogens. But although we draw the polymers in a straight line when we're drawing it on paper, in reality the carbon chains are kinked, and so we can draw it like this, where the vertices are carbon atoms and the straight lines are the bonds between carbon atoms. And usually polyethylene is made where in reaction conditions such that you don't get very much branching, and so all the polymer chains are long and shaped similarly like this, and so when they are packed together they pack closely, because they can all fit in nicely, very closely to each other. So these straight lines, as you know, representing covalent bonds, which are strong, but between the molecules are just van der Waals forces, right? So, which you'll have done in bonding. So between the particles, the polymer chain molecules, just van der Waals forces, which, as you know, are weak forces. They're not anywhere near. They're about 1/100th of the strength of a covalent bond. But in the case of polyethylene, because the chains can get so close to each other, then they're bonded reasonably strongly to each other, right? So the result of that is that they're quite dense, right, and quite strong by plastics standard. So they're strong and rigid, and have a reasonable density. So this would be high density polyethylene, and that's the sort of plastic that's made, for example, your bins are made of. So if you can, think of a bin in a lab or a bin at home, plastic bin would be made out of high density polyethylene. You can make low density polyethylene by changing the reaction conditions and introducing branches which separate the molecules. But high density polyethylene is an example of strong rigid plastics where the polymer chains are closely packed together. So next we're going to have a look at the opposite of high density polyethylene, where the polymer chains can't pack so closely together. So in this case, let's have a look at polystyrene. Polystyrene, and you'll be familiar with polystyrene from packaging materials, and if you've unpacked like a laptop or a television or anything sort of precious, you will be familiar with polystyrene. That's aerated polystyrene, so it's even lighter than it would be normally, but polystyrene, even before it's aerated, i.e. Fed with air bubbles, even before it's aerated, it's still quite light, and that's because the polymer chains can't get very close to each other, so there's some more space involved in the structure. So let's have a look at the monomer. The monomer of polystyrene is called phenylethene. All right, so we've got an ethene, a molecule that starts off looking quite like ethene. So you've got hydrogens here, and let's say another hydrogen here. But one of the hydrogens, this hydrogen here, is substituted for a phenyl group. And you draw a phenyl group like this. It's a hexagon we draw it like that with a circle in there, and you'll learn in due course that that circle is 3 double bonds that are distributed around across all 6 of the carbon atoms. So each of these points that I'm just drawing dots on, they represent a carbon atom, and in this case you've got one hydrogen atom that's coming off each of the carbon atoms, which we don't draw, right? So each of them would have a hydrogen atom like so, but we don't normally draw it. We just we know what we mean when we draw this hexagon with a circle in it. Okay, so this monomer is called phenylethene. That's phenylethene, all right, because it's based on ethene, but one of the hydrogens has been substituted for a phenyl group or a benzene molecule, and when that polymerizes, you get the polymer that we're going to draw like this. So our 2 carbons, that was our double bond, it's now a single bond after the addition reaction. We've got 1 hydrogen, so that's this hydrogen that I've just drawn. Going to draw the bond that is going to connect the repeating unit. We've got another hydrogen down here. I'm drawing it upside down. This is another hydrogen, and we need to put our phenyl group in there. So we're going to draw that like so. We've got the bond that's going to join the repeating unit. We need our curly brackets, and we're going to have n of those repeating units because we start off with n of the monomers. And when we want to name this, we're going to, if we were naming it strictly, it's a polymer now, so we're going to start off with poly. We are open brackets, and we give the name of the monomer, phenylethene. Phenylethene, like so. So that's the strict name that's the IUPAC name for polystyrene. And again, the reason we're looking at polystyrene is that because we've got a less dense, lighter polymer, which for some applications is very good, and it's light and less dense because the substituted group, which in this case is a phenyl group, the substituted group stops the polymer chains getting close to each other, and then the van der Waals forces are weaker, and the particles therefore, the chains therefore are further apart and less strongly attracted to each other, so they're also more flexible. Alright, and that's because, draw that upside down trio of dots, because the chains, the polymer chains, less closely packed, right, and also weaker van der Waals forces, because of that more separation between the polymer molecules. Okay, so that summarizes polystyrene, which illustrates a polymer that has different properties from HDB, high density polyethylene, for example, this one being light and flexible. So now we're going to have a look at a polymer that is not light and flexible, but instead is quite hard and brittle. So let's write that in. Hard and brittle, which is good for some applications. And we're going to have a look at polychloroethane, or PVC. Polychloroethane, and we put our brackets around the name of the monomer. Let's also put its common name, which is PVC, polyvinyl chloride, and that starts from a chloroethane monomer. Okay, let's draw out the chloroethane monomer. So we've got our two carbons with a double bond as usual, with a hydrogen, but the fourth hydrogen is substituted by a chlorine, which you'll remember is electronegative. So that's what's going to lead to the difference in properties. But first, let's just name this. So this is chloroethane, and if we had n of those, we would be able to draw our polymer in the standard way. So again, we've got our two carbons, but this time with a single bond, and we've got our two bonds that join our repeating units together, and we can put our brackets in that say we're just talking about the repeating units, and then draw the repeating unit itself. So we've got hydrogen, the two top hydrogens, and we've got hydrogen and chlorine. And we've got n of those repeating units all joined together, and that's how we draw the polymer, which we name as polychloroethane, like so. Now we mentioned that that the chlorine was electronegative and drew electrons towards itself, giving it a partially negative charge, leaving the carbon that it's bonded to partially positive. And we can represent this diagrammatically by looking at a polymer chain as a zigzag line, as usual. And you might have a chlorine coming off this carbon here. All right, and the chlorines are partially negative, and the chlorines happen on every other. It's supposed to be a little triangle, sorry about that. Every other carbon, so that's another delta negative chlorine there, and the carbon that it is that they're bonded to, we can put a little delta positive in there and another little one in there. And let's put another one there to complete our picture. So we've got 3 repeating units there with 3 delta negative chlorides, and let's draw the same an identical polymer molecule adjacent to it. So you could draw it like this. And this would be our chlorine delta negative. That would be our chlorine delta negative, and that would be our chlorine delta negative in this case. We would have our delta positive carbon atoms on these 3 corners, and you can see we're going to have attraction, electrostatic attraction. Let's put that in green. So you can have electrostatic attraction between the delta positive carbon and the delta minus chlorine. All right, and that would be called a permanent dipole-dipole force, which is a reasonably strong bond. So let's draw that out. Permanent dipole-dipole, which is stronger than van der Waals force, right? Which is what makes this type of polymer, this PVC, it makes it hard and brittle, right? Because of those stronger bonds between the polymer chains. And so the applications for that would be things like window frames, and some drain pipes, where you need a hard plastic. So you need it to be quite light, so it's still quite light because it's plastic, but you need your window frame to be quite strong and stiff, in which case most window frames now are made out of PVC or polychloroethane. Okay, so that's the third example. That's the third plastic we've looked at. Each of the 3 have different properties because the way that the polymer chains interact together. Now we're going to have a look at a 4th way of changing the properties of plastics, and that is plasticizers. And plasticizers are small molecules plasticizers like that are small molecules, and they're small molecules that fit in between the polymer chains. They fit in between the polymer chains, and because they sort of squeeze in between the polymer chains, they would reduce the van der Waals forces between the polymer chains and therefore make them more flexible. All right, so this leads to the plastics being more flexible. And so, for example, if you use plasticizers with PVC, you know from the previous slide that PVC is hard and brittle, but if you introduce plasticizers into PVCs, PVC plus plasticizer, then you get a very flexible PVC, and that would be the PVC that is used in clothing, for example, like fake leather jackets or very tight fake leather clothes. So let's just complete our writing. Plus the plasticizer plus plasticizer used in clothes like fake leather. Because the bonds between the polymer chains are much weaker, it's therefore flexible. And another example would be electrical cable. Electrical cable. So the plastic that goes around the copper wire in an electric cable is made out of plasticized PVC. Obviously needs to be quite flexible because the wire is going to go round corners, and that would be because of the plasticizer forcing the molecules apart. There, hopefully that's been clear for you. 4 ways of changing the properties of polymers, and a reminder of the addition reaction of alkenes.